Welcome. My name is Eberhard Morgenroth. I'm a professor at ETH Zurich and at EABAC, the Swiss Federal Institute of Aquatic Science and Technology. This series of lectures will provide you with an introduction to biofilms and how biofilm reactors can be applied for biological wastewater treatment. Why are we interested in biofilms? Let us start with taking a look at nature. Here's an example of a beautiful biofilm in a hot spring in Yellowstone National Park. What do we see? The bulk water looks crystal clear. The reason is that bacteria cannot survive growing in suspension under the harsh conditions in the hot spring. The beautiful colors result from bacteria growing in biofilms. Protected in the biofilm, bacteria are able to thrive in the hot spring. Thus, for the microorganisms, there can be significant benefit to organize into biofilms. The question is, to what extent we can benefit from biofilm lifestyle for wastewater treatment. In this course, we will jointly explore biofilms and biofilm reactors for wastewater treatment. At the end of this current module, you should be able to explain differences and similarities between biological treatment processes using biofilms or suspended biomass. Discuss how mass transport limitations influence substrate availability inside the biofilm, and in turn how substrate availability influences active biomass. And finally, this module should provide you with an overview of what to expect in the overall course on biofilms and biofilm reactors. Biological wastewater treatment is in many ways replicating what we observe in nature in a technical system. Here are two examples for how microorganisms grow in nature. On the left, you see a lake, where microorganisms grow predominantly in suspension. On the right, you see a flowing river. Now, imagine that you have to cross this river and you step on these rocks that make up the riverbed. Most likely, these rocks will be very slippery. What makes these rocks slippery are biofilms growing on the surface of the rocks. But why do bacteria choose to form biofilms on these rocks? It is simple. Bacteria growing in the flowing water would quickly be washed out of the system. On the other hand, bacteria that attach themselves to the rock surface can retain themselves in the system. Let us now turn to engineered treatment processes inspired by these natural systems. In activated sludge systems, the biomass is suspended in the aeration tank. To avoid washout of suspended biomass, activated sludge systems require a secondary settler. Sludge in the secondary settler is recycled back to the aeration tank. In contrast, on the right we see a trickling filter that has much in common with a riverbed. Much like a river, water flows, or rather trickles, down the rock material. Biofilms grow on these rocks. The biofilm retains bacteria that degrade contaminants from the water that is flowing past the biofilm. What can we learn from these simple examples? Number one, a key feature of biological treatment processes is to avoid washout of bacteria from the systems. In an activated sludge system, this requires a settler. In the biofilm reactor, bacteria are retained by attaching themselves to a surface. Number two, for the biological treatment to work, biofilms have to be exposed to the contaminants, which is food for the bacteria. And number three, bacteria must have access to a suitable electron acceptor, for example, oxygen or nitrate. If these three requirements are met, then similar treatment objectives can be achieved in activated sludge and biofilm systems. And in both types of systems, treatment is achieved with similar microbial functions that are performed by similar types of microorganisms. Then, how are activated sludge and biofilm systems different? Biofilm systems can often achieve higher biomass concentrations compared to activated sludge systems, and therefore biofilm systems can often be more compact. But as we will see later in this course, higher biomass concentrations also mean that there is more competition between bacteria. And it can be more difficult for substrate to reach bacteria growing deep inside the biofilm. Next, we will explore an example comparing biomass concentrations in activated sludge and biofilm reactors. This is a schematic of a biofilm reactor. In this example, we will calculate the amount of biomass per reactor volume. We calculate the biomass per reactor volume from multiplying the specific surface area of the biofilm carrier, the biofilm surface area per reactor volume, with the biofilm thickness and the biofilm biomass density. Here I'm using typical values for specific surface area and biofilm biomass density. The assumed biofilm thickness in this example is rather large. The total amount of biomass in this example is 13.5 gram volatile suspended solids per liter of reactor volume. If we compare the 13.5 gram VSS per liter with typical biomass concentrations in activated sludge systems, then we can see that biofilm reactors can have significantly higher biomass concentrations compared to activated sludge systems. But to what extent will bacteria in this thick biofilm have access to substrate and oxygen? To evaluate the effects of mass transport limitations, we will be using a one-dimensional biofilm model throughout this course. What are the relevant features we need to consider? We have a solid support medium for the biofilm. This could be a rock in a river or a biofilm carrier. A biofilm grows attached to this solid surface. Outside the biofilm, we have the bulk water. The bulk water is assumed to be well mixed. The only way that bacteria in the biofilm have access to substrate is by diffusion, where substrate diffuses from the bulk to the biofilm surface and then further into the biofilm. Local substrate concentrations within the biofilm will depend on the balance between the rate of diffusion and the rate of degradation. So let us now plot some examples of possible substrate concentrations inside the biofilm for different rates of degradation. Here is a coordinate system showing substrate concentrations over the thickness of the biofilm. We assume a given substrate concentration in the bulk water. In case there is slow or no degradation of the substrate in the biofilm, substrate can diffuse all the way into the biofilm. Biofilm concentrations will be very similar to bulk phase concentrations. Now, with increasing rates of substrate degradation inside the biofilm, it will become more and more difficult for diffusion to keep up with degradation. The balance between diffusion and substrate removal by reaction results in the following concentration profiles. Substrate will be able to penetrate less and less of the biofilm with increasing rates of degradation. Now, let us go back to our example. Here we had assumed a 1,500 micrometer thick biofilm. For such a thick biofilm, it can be expected that only the upper layers of this biofilm are penetrated by substrate. If only the upper layers of the biofilm have access to substrate, then only in these upper layers bacteria will be able to survive. Bacteria closer to the base of the biofilm will decay, leaving behind inactive biomass. For this 1,500 micrometer thick biofilm, most of the biofilm will be inactive or dead biomass. What does this mean for the biofilm reactor in our example? most of the thick biofilm is not contributing to substrate degradation. If we compare substrate degradation in our thick biofilm with a much thinner biofilm shown at the top, we see that both biofilms have the same amount of active biomass. What this means is that per surface area, we can expect the same substrate removal rate for both biofilms. This simple example demonstrates what we observe in most biofilm systems. Substrate degradation is not limited by the total amount of biomass. Instead, the available surface area and mass transport of substrate into the biofilm limit overall performance. The trick in designing and operating biofilm reactors will be to manage biofilm thickness so that biofilms are sufficiently thick, but not much thicker than the penetration of substrate. We can now complete our simple example. If only 10% of the biofilm are exposed to substrate, then only 10% of the total biomass in the system will be active. Thus, we have to be careful when we compare biomass concentrations in biofilm reactors with activated sludge systems. Let us now take a look at the overall course. What can you expect to learn? In the next module, we will discuss how to link microscale observations of the biofilm with overall reactor performance. Then I will provide a broad overview of different types of biofilm reactors and their main design features. Next, we will look at mathematical modeling of biofilms and biofilm reactors. Mathematical modeling helps us to identify factors limiting overall reactor performance. Last, we will discuss an overview of practical design approaches for biofilm reactors. Here are the take-home messages for the current module. Adding a carrier material to a reactor allows to grow and retain bacteria in a biofilm. Biofilm reactors do not require a settler to keep active biomass in the system, but solids removal is required to prevent detached biomass to get into the effluent. Biofilm reactors can have more biomass per reactor volume compared to activated sludge systems, but the biomass in the biofilm may be inactive due to diffusion limitations. Now, my hope is that this first module motivates us to study biofilms in more detail in future modules.